Hello, welcome to the final presentation of the ImechE Challenge Repeatable Vehicle done by Team AB17.
Firstly, the main goal of this challenge was to build a repeatable vehicle that moves towards a wall, touches that wall, and returns to its initial position as close to the target as possible. The distance of this vehicle relative to the target will be determined by the position of a brass-plated hook attached to our device.
So initially what we did is that we brainstormed different ideas of the vehicle. So for example, for the drive mechanism, we decide that we're going to use a motor to drive the vehicle. The vehicle is going to be having four wheels. What kind of gear ratio that we need to use for the vehicle, the torque produced, the speed, and of course, we considered some other aspect, as you can see in this mind map.
We then drew some sketches to help visualize our ideas. Initially, we implemented a threaded rod with a support structure containing a sliding nut that moves past the main switch until the vehicle reaches the wall. When the reverse switch is activated, it reverses until it reaches the kill switch, where it stops the device at the bullseye. However, to reduce cost and complexity, we thought about using a rack and pinion system, where the piston would move along the rack a precise distance and return the vehicle exactly at the bullseye.
So for the assumption we made, we assumed that the drag and the rolling resistance to be negligible because they were calculated very small, and we did some basic research and assumed the efficiency percentage for both gear train and the motor to be at 70%. So therefore the overall efficiency of the driving mechanism is 49%.
So initially we'd start the calculations by setting a target time within which we wanted to complete the challenge, calculating the average velocity at which we'd need to travel to achieve this, finding the wheel RPM, assuming no losses. Then, assuming losses, we'd work out a gear ratio, and we ended up concluding that we'd need a 1 to 108 gear reduction. We proceeded in a similar manner to find the timing system gear ratio and estimate the minimum length of the rack. So from the final design sketch layout, we see the motor that drives the gearbox driving the rear axle. We utilize the motion of the rear axle to power up the mechanical distance measuring device for another gearbox of 1 to 5 reduction. This drives a rack back and forth depending on the motion of the vehicle, and when the vehicle reaches the bullseye, the rack is supposed to move forward and flick the switch off. Now, concerning the reversing switch, we have it mounted in the front of the vehicle behind a spring and push rod assembly to cushion the.
The mathematical model created gives a good representation of how the velocity and acceleration change with time. These variables are dependent on things like torque and RPM. By adjusting some values, we were able to finalize a functional model. These performance curves were created from the model. The device's position changes linearly with time. The velocity changes rapidly with time and reaches its maximum value quickly. Similarly to this, the acceleration of the vehicle drops off at a fast rate.
Going through the mass model, we finalized those numbers. Our gear ratio is 1 to 108. Our top speed is 0.143 meters per second. Our time to reach top speed is 0.27 seconds. Our maximum acceleration is 13.503 meters per second squared. Our maximum wheel torque is 0.333 newton meters, and our maximum wheel RPM is 27.2. So here is our 3D model and how everything is laid out. Our front wheel is just a bit at the back so it can tune for our bumpers and mechanisms, and our battery is just right in the middle.